All right, so far we have looked at the mathematical equations governing the BJT, right? Now, with any device or any electrical component that you have studied so far, resistors, capacitors, inductors, electronic devices, diodes, BJTs, FETs, they're all ideal models, right? Every equation that we've looked at, we consider that the device is going to be ideal. So today, what we're going to look at is some properties of the BJT, where it modeled the non-ideal or the real behavior of the BJT. Plus, we'll also look at a couple of quantities which focus on the non-linearity or non-linear parameters of the device. Okay, like a resistor, capacitor, inductors are linear devices. Diodes, BJTs are non-linear devices. So we look at non-ideal and non-linear behavior of the BJT. So the first up is the junction breakdown voltages, right? Obviously comes from the fact that a PN junction is a one-way device, conducts current in the forward bias and is off or does not conduct in the reverse bias. So in a transistor, in a BJT, we have two PN junctions, whether it's a PNP transistor or a NPN transistor, we have two PN junctions in there. And so we can look at two junction breakdowns. In both cases, we should not be seeing any current whatsoever in reverse bias if it's an ideal device. Obviously, it's not an ideal device, so we'll see something. All right, let's B minus V. Oh, sorry. Minus V minus I. Minus V minus I. So I'm drawing the reverse breakdown characteristics of either the base emitter, or the base collector junction. Now look at the graphs and tell me what difference do you notice? So we have this over here. What would that indicate? There's some distance between the data points. Okay, let's say it's a large distance. But both graphs are basically reverse bias PN junctions. They look very similar. Which one do you think is the base emitter? The one on the left or the one on the right? I have one left. Do I have two lefts? Okay, I have one right, one left. Anyone else? No bids? And going to the left. All right. This is the base emitter. And this is the base collector reverse bias junction. Yes. No, it's a reverse bias PN junction. We're just talking about reverse breakdown. So it doesn't matter whether PNP or NPN, the discussion would apply to both. So now that you know the answer, think for this for a few seconds and think why that might be the case. Both junctions are reverse bias. The base emitter is also reverse bias. Collector base is also reverse bias. We're not looking at device function in any way. Right now, we are simply looking at the PN junctions. But why are the two PN junctions, even though both of them are reverse bias, why do they have slightly different values? Yep, the answer is the emitter is more heavily doped. And if you think back to the previous chapter, which diode has heavy doping? And so this has Zener-like characteristics. Okay, so the base emitter junction behaves like a Zener diode in reverse bias. Not behave exactly like a Zener diode, but have that kind of reverse characteristics in reverse bias. So in the lab, at least in my lab section, what I like to do is at the beginning of the lab, you would take the transistor. No need to, I mean, say no need to look at the spec sheet. That's the wrong advice to give to students. But before you look at the spec sheet, we can use this to determine the pinout of your transistor. Okay, so in the lab, the base for a transistor would be in the middle. You have 3 pins. The middle pin would be the base. The other 2 pins would either be the collector or the emitter. We don't know which one is which. So what we will do is we'll take the base. We know it's an NPN transistor. So we will reverse bias the base with either the collector or the emitter junction. Then we look at the characteristic. If the junction breaks down within 10 volts, then that terminal is the emitter. If it doesn't break down for 10 volts, then that junction is the collector. The collector junction will not break down until probably greater than 50 to even hundreds of volts. I would say 50 volt at a minimum. High current transistors, probably hundreds of volts. Okay, the junction should not break down because in the active mode, the collector base junction is reverse biased. So if it starts conducting in reverse bias, well, it's not going to work as a transistor, right? Not work as a BJT amplifier. So again, the theory would be that the emitter is very heavily doped. So the emitter base junction in reverse bias would function as a Zener diode with characteristics similar to a Zener diode. So in the lab, you can use this theory to determine the pinout of your BJT. You connect it to sweep and go, connect the base to the positive terminal, apply a negative voltage corresponding to the other terminal, the other unknown terminal. If you see a breakdown in the junction, meaning a current progressing in less than 10 volts, that terminal is the emitter. If it does not, then it's the collector. Make sense? Let me know if you have any questions. Yes. So the question being asked is if the BJT is in forward active mode and the collector base junction is forward bias, which would be true, the junction does not break down. The answer is yes, it does not break down. We still get a good amount of current flow through. Because, and this leads us to the next point, which is the base transit time, because the charge carriers that are coming from the emitter would be the minority carriers in the base. Okay, if they're the minority carriers in the base, the minority carriers can cross over to the collector if the junction is reverse bias. Again, that's going back a few lectures. Collector base junction is reverse bias for active mode. The reason current can work is because the minority charge carriers, the charge carriers coming from the emitter crossing over into the base would now be minority carriers. And so they are able to cross over because in reverse bias, it's only the minority carriers that cross the junction. The majority carriers are actually pulled away. So it's an NPN transistor. Electrons cross over into the p-type base. They are the minority carriers. And now the base and the collector junction is reverse bias, so the electrons can cross over. If it's a PNP transistor, you have holes coming into the base. And when holes come into the base, they are now the minority carriers because it's a PNP transistor. And again, collector base junction is reverse bias, so holes can cross over because we have collector current flowing through. So yes. NPN. So emitter is N type, meaning electrons come into the base. Yeah. So continuing from that point. So the charge carriers coming from the emitter into the base, they're injected into the base. So now the base stores the charge. And then when you have the reverse bias, they are pulled into the collector. So the amount of time it takes for these charge carriers to transit through to the base and through to the collector is known as the base transit time. So it was a very good question to lead into the next point. So the base transit time is effectively the amount of time that is taken by the charge carriers to transit the base and go from the emitter to the collector. So BTT is labeled as tau F, and tau F can be given by the equation WB square divided by 2VT mu n, where WD is the width of the base, the physical dimension of the base. VT, of course, is the thermal voltage. And mu n is the carrier mobility. In this case, electrons for an NPN transistor. And the same equation for a PNP. With mu p, mobility of holes. Okay, mobility of holes. So key things. Transit time is directly proportional to the base width. I mean, the width of the base, obviously, farther you have to go, the longer it's going to take. Inversely proportional to the thermal voltage and inversely proportional to the carrier mobility, which means if your transistor is, if the charge carriers, primary charge carriers in your transistor are made out of electrons, not made out of, are electrons, then the transit time, the speed is faster, so transit time is lower. Versus holes, where the transit time is larger or higher because the mobility of the holes is less than that of electrons, which means that NPN transistors are twice as fast as PNP transistors for the same physical geometry and the same doping profile. And this is the reason why. Actually, it's more than twice as fast. It's 2 to 2.5 times faster. Electron mobility was about 1500, and hole mobility is less than, I think, approximately 1/3. Okay, so it's inversely proportional to the carrier mobility. If the carriers are electrons, then transit time is less. If the carriers are holes, transit time is more, relatively speaking. Hence, NPN transistors are faster than PNP transistors. And because of the mobility, it also places an upper limit on the frequency of operation, or max frequency of operation. Would be 1/2 pi tau f. Okay, 1/2 pi tau f. See, when we did our, yes, go ahead. Mm-hmm. Yes, that is applicable. The point being made is that if the frequency of the signal that's being applied to your BJT circuit is higher, I mean, has a time length shorter than the transit time, then it wouldn't be able to work. So that would be correct, yes. So high frequency devices are not made out of silicon, made out of different material. Gallium nitride, arsenide, faster semiconductors. All right, so charge is going from the emitter, I mean, sorry, not charge. Charge carriers are going from the emitter to the base. The base stores the charge, which is then injected or moved into the collector, right? And then we have current flowing through the BJT. So this charge that is stored in there gives rise to a capacitance between the junctions, and this capacitance is known as the diffusion capacitance. Okay, diffusion capacitance. The diffusion capacitance can be given by the equation CD is equal to IC over VT times tau F. Okay, IC times IC over VT times tau F. So it's a function of VBE, the base emitter voltage. And there's a small derivation and explanation in the textbook. So everything that we are discussing today, there are small sections in the textbook. That's part of the assigned reading. So please make sure you keep up with the assigned reading in the book. Okay. The IC over VT parameter that you see here is also the transconductance. So transconductance would be how is the collector current changing with respect to change in the base emitter voltage, IC over VBE. Okay, IC over VBE. And again, there's a small derivation that explains how we arrive at this equation. Collector current over the thermal voltage. And you will do this in the lab, and we will try to obtain, or one of the calculations at the end of the lab is to determine the transconductance from our experimental values. If you're lucky enough, we might get a close enough value, but as always the case, there are also other factors that go into determining the exact values. But this is the equation you would use. Okay. And then finally, we have the beta cutoff frequency. So beta cutoff frequency is the upper limit of the current gain beta, right? The frequency of operation for a transistor. So, so far we have looked at beta as a constant value, right? We have not looked at it as a function of the frequency or the operating frequency. If you define beta as like 100, we simply assume that it's ideal, and for the entire range of frequencies, doesn't matter whether it's 1 hertz or 1 megahertz or 1 gigahertz, we just assume that beta is going to be the same. But that's not really the case. So again, non-ideal, there is a upper limit for the beta cutoff frequency. And that is given by this equation. And I will explain every term in here. So 1 plus F over FB, the whole square, where FB, the beta cutoff frequency, is given by FT over beta F. Okay. And then your graph would look something like this. All right, so as I was saying, we assume that beta is going to be constant. And it is up to a certain point, probably not this long. Okay. But then it's going to start dropping off. Okay, it's going to start dropping off. So as the frequency increases, beta is going to remain constant for a long period of time until it crosses the upper limit. That upper limit is defined as the beta cutoff frequency, and will be somewhere here. After which point it will start dropping off in value. Okay. And that's the cutoff frequency. FT is the unity gain frequency, or the frequency at which beta value is equal to 1. Okay, it's the frequency at which the beta value is equal to 1, unity gain frequency. And that would be part of the spec sheet defined by the manufacturer or given to us by the manufacturer. So if you look at the equation, this graph represents the values determined from this equation. Beta, the current gain beta as a function of frequency is beta f divided by square root of 1 plus f over fb the whole square. Beta as a function of the frequency f. So f is the variable, the unknown variable, right? FB is the beta cutoff frequency, which you obtain from ft over beta f. Beta f is simply the beta value that we obtain in the forward active mode. Okay, so lowercase f is the frequency, uppercase f is for forward active mode. So ft over beta f gives us the value for fb. We plug that into the above equation and we can obtain the value of beta for any given frequency. Okay. All right, so let's take a pause. Let me know if you have any questions. Yes. So the question being asked is, why does it decrease, right? And you yourself gave one part of the answer, is that, yes, because of the transit time, there's an upper limit on the amount of current that could, the amount of charge carriers that can transit through the BJT, and which basically means the current would be dependent on that frequency. Yes. All right. Any other questions? Okay, so we'll end class here today. We'll pick up here on Wednesday. And Wednesday, we should be able to wrap up everything else in the chapter. And then we'll solely look at circuits and different kinds of circuits and circuit analysis using BJTs, MOSFETs, diodes for the rest of the 2 weeks. Okay, rest of the 2 weeks.